Let's see if anyone joins me. I am doing my best for that. It is, I haven't made it, I haven't linked it into the, I'm so far behind. I have not put it into a daily agenda. Yes, it will be. Yes, it will be. Correct. You will have it. You haven't got it yet, but you will have it. It's coming. Hello, Dr. Newsom.
Hello, how's it going?
It is well. How are you doing this fine day?
Doing awesome.
Grand to hear. All right. I should probably turn on an external camera for the children so they don't have to stare at my bulbous head. Let's see. There, so that you can believe that I am in. Oh, he wants it. There we go. There is a class out here. See no evil, hear no evil. Okay. We'll wait a few minutes. We'll wait 1 minute so that I don't delay anyone further. Rybak, Dr. Rybak, how are you today? Oh, you are front and center. Oh, I love the crown, ma'am. All right. Ms. Diaz is here, so we are just waiting. I believe Stafford is going to have a substitute teacher, so we will see that. And Dr. Peppers, we should have him in here as well. 1 more minute, and then we'll get started on our new lesson today, new topic.
It's an old topic newly presented.
Thank you. Yes, it is old as time, I'm sure. Well, okay. It appears that the other two may be off on their own accords, so we shall proceed without them. Thank everyone for coming to the presentation today. What we are going to talk about is a big fancy word. It is thermodynamics, but the reality of this topic is you could boil this down to heat. This topic is all about heat. Let me change my camera so that you can see me and the kids can focus on themselves now. All right. So what we need to understand for today, one big goal for us is learning how to utilize one simple formula. Now, there are multiple ways in which we can calculate heat. However, today we're just going to talk about one of those methods and focus in, drill in on that one. And we're going to make it relative to you. It's going to be something that you're going to then understand and hopefully start to put a perspective on what you eat. That's my other spin on this one, is to make this actually something that you can appreciate in your real life. Okay, so here we go. So again, as I had stated, the goal is to learn this formula and to understand what actually heat is. If we recall back from the beginning of the school year, we have this focus on chemistry as being a study of matter, not as a general word, what matters, but as everything is made up of matter. And we divided it into different solutions or into atoms and molecules. And then we started breaking those down and we learned how to put them back together and how to name them. And that's been our focus here for about 6 months. And now what we're doing is we want to figure out what happens. How do we cause these atoms to now break back apart? And that's essentially what we're trying to learn about with heat. So if we understand that matter can be altered in one of 2 different ways, through physical means or through chemical means, hold on just a second, let me put my speaker up here. Then what we can start to understand is that you can alter matter through physical processes, which doesn't actually change its formula, or we can do it through a chemical process. And that's what we want to focus on. But really quickly, just to remind you, this is just a physical process. This is an artisan Yes, and so if we were to then compare that
I'm Ron
to a
Pitts,
physical.
and you're about
Oh
to
my
see some
goodness.
of the most astounding moments of destruction ever caught on camera.
What?
With every second that passes, the fire grows.
Oh, the shut. Nobody heard that.
What they don't know is that the inferno now threatens a storage area where 6 million pounds of the rocket fuel is held. If the chemicals exceed 716 degrees Fahrenheit, the entire area will combust. Then the unforgettable.
Oh, no. Whoa. All right, that is a chemical reaction at its finest there. So what we see in that one is that jet fuel has become
Pitts.
something.
You're about
Oh,
to see
Ron,
some
we
of
already
the most
heard from it.
astounding
Sorry.
moments of destruction.
We can, yes, at home, not here. And so we need to remember that that bar that you saw, that is the manifestation of energy. It's not something that you can necessarily capture and put into. It's not like a lightning bug that you can and just hold on to it and then you have this eternal glowing flame or something like that. It's energy. And so we are taking matter and converting it into energy. And so this recalls back a day at the beginning of the year, whenever we talked about the law of conservation of matter. You can neither create nor destroy matter. Well, similarly, we can neither create nor destroy energy. We'll talk about that one in just a second. Well, it was Einstein who famously comes up with this concept of how we can relate matter and energy through his equation E equals mc squared. I need a little help out here. What does the M stand for, do you think? Mass is absolutely right. And then someone on the broadcast, yell out for me. What does the C stand for? Yeah, that's
Speed of light, somebody said here at Ford.
light is correct. So energy is in fact matter that's moving. So we have now a relationship. If we can measure matter, we can actually measure how much energy it has. And that's where we're headed with today's discussion, because we know how to measure matter. Well, now we can convert that concept into energy. So that's where we're headed with heat. So if we need to investigate energy, we need to understand that there are two different versions of energy. There is stored energy called potential energy, energy of your position, and there is kinetic energy. And you're saying that's great for a red sphere that you're holding precariously over a cliff, don't fall off. What are we going to do with it in chemistry? Well, you have to understand that that stored energy are the bonds in between the atoms. So if we can rip those apart, we can free up the energy. That far that we saw in that chemical plant, that doesn't happen by accident. That's because simultaneously, all of these tiny little atoms are being ripped apart, and they are releasing their energy. That's kinetic energy. We then see it as that shock wave that went out from the explosion, or we see that as the fire that was blazing from afar. Now, it's not the only form of energy that can exist out there. We are only going to focus on the thermal energies aspect of it, but there's other energies that are out there. Like I said, there was that sonic boom that came out from the explosion. There's mechanical energy. Every time we drive somewhere, we are harnessing that. Well, I'm sorry, that's kinetic energy and mechanical energy altogether. We could even be environmental about this, and we could start talking about the solar panels and renewable energies in that sense. Wind energy. We could talk about our nuclear energy. We might actually get around to discussing that with some of the classes if you haven't already. So, full circle. If we understand that matter is related to energy, then the concept that we can neither create nor destroy matter applies also to energy. We can neither create nor destroy any kind of energy. This is called the first law of thermodynamics. Now, what it's not said in here is implied by the arrow, that we can transfer energy, though. Now, that's new. We didn't talk about that with matter. Yes, you can move matter from one location to the next, but energy actually is transferable. So it can move from one object to the next. How does it move? One of three different ways. You have convection, which is heat that is moving through a fluid. In chemistry, fluids are not relegated just to liquids. It can be liquids and gases. Those are both combined together to the same concept of what a fluid is. Conduction, that's whenever there is physical contact between two objects and the heat is transferred through direct contact. And then there's the radiation, and that's how we feel the heat from afar. And so that energy particles, radiation particles are hitting our body, and we perceive that as heat. Now, I need you to not get confused. This is one of the biggest misconceptions of the public, hopefully not of a somewhat highly educated, gifted classroom. Energy is heat, is a measure of heat, but heat is not the same thing as temperature. Now, we don't have heatometers out there. There is not a physical means for us to measure heat. So we have to sort of indirectly measure it. So when we talk about heat, we're actually going to end up measuring temperatures most of the time. The units of heat are in something called a joule, Joules. They are so small, so insignificant that if you were to rub your hands together, you're creating about a joule of heat right there. So that doesn't take a whole lot. And so that's not enough for you to power your house, a lamp even, something like that. So a joule probably more than likely will be in the scope or in the scale of kilojoules. That would be more of a measurable quantity. Temperature that we're going to indirectly measure this energy and heat from, it's in one of two different scales that we're familiar with, either Celsius or, well, one of three, Celsius or Kelvin in the science classroom. Outside of the classroom, we talk about it being in Fahrenheit. Like today outside, it's in the nice 50s. It would be in the teens if we were talking about it in Celsius. So what we now have to understand then is how the heat and temperature relate. Because if we're going to measure heat based on temperature, we need to have a little bit of a perspective. This will be the first time that you see this heating curve. And it's so poorly worded. I understand that curve implies that it should be nice and, you know, curvy. Yeah, rounded. It should be parabolic or something like that. But for whatever reason, chemists didn't go to math class, I suppose. And so this jagged stair-step graph is what we will call a heating curve. Now, this graph could also take a staircase down to the basement and it would be a cooling curve. But in a general sense, we just call this a heating curve. We will examine this next class with a little bit more specificity. But for today, all we've got going for us is just an understanding that heat can be added together to change the temperature. So we can add more heat, we can change the temperature, which consequently also changes the state of matter if we add enough heat. Now, if you happen to be unaware that, or you need proof that heat can transfer, all you need to do is be in a relationship with another individual. And eventually you'll feel that little spicy nugget in your back of your head, and it says, oh, I want to touch that person. And so you do, and you find out that one of you is cold and the other one is a little bit more hot. And it just always happens. It's very rare that you would have a situation where both of you have equilibrium as far as your body temperatures are concerned. Yes, I agree. I see some snickers out there, and some of you are saying, oh, it's easy for you to figure out who's hot and who is not. And so, you know, whenever you are like in this relationship like my wife, you know, after a few years, you're like, I don't want to hold your hand because you're cold and bitter. And it's not because she doesn't have a heart. That's consequential. That's just subsequential. That's not true, because I'm sure in her world, she is saying, oh, you're the grossest, clammiest, wettest, nastiest thing. I don't want to touch you either. And so there's someone who's hot, there's someone who's cold, and the heat is always going towards the colder temperature. The second law of thermodynamics, this is a freebie for you, is that energy always wants to spread out. It always wants to go to the path of least resistance. It's always wanting to go towards chaos. That was a bonus one. You didn't need to know that one, but it's there for you. So if we understand that heat is always moving some direction, well, then we need to give it a classification. If you are taking in heat, if you're the cold one, you're taking in heat, you're stealing someone else's heat, You don't have a heart. No, I'm just kidding. You are endothermic, and I know that that's backwards. It totally is, that the cold object is endothermic, because in your head, you're saying, well, if you're taking in heat, that means you must be hot. No, it's the exact opposite. Because you're cold, you are stealing heat. And just the opposite, if you are hot and you are giving off heat, then you are your exothermic. So got to get those two straight. Exothermic means you're giving off heat. Endothermic means you're taking in heat. All right. Oh, and if you didn't believe me, here is proof of how weird this scenario is. All right. So we put water, and then we put some chemicals in a beaker. And there's proof it's room temperature. We add a second chemical, and we add a little water. We stir it. I think it's in the way. And what we see is it's starting to go down in temperature. Well, that water we put on there froze. It froze because it stole the heat from the water. That chemical reaction was absorbing heat. And so it absorbed the heat from the water. How much? Well, it's pretty interesting. It's very solidly frozen. All right. Here. Get it? All right. Let's go back to the slideshow. Hold on. And if you're saying, okay, well, that's endothermic. Come on. Well, then here would be your exothermic reaction. And it will be typical. It's what you know and love as giving off some heat. It'll be obvious to you. So we have some potassium permanganate and a little bit of iodine droplets. And eventually it starts a purplish pink fire. Woo! That was exciting, and not as exciting, I know, as the chemical plant, but it's proof that there exists this scenario of heat transfer in a reaction. Okay, I alluded to at the beginning the fact that all this is going to culminate in one formula. We are going to be solving for heat. Here's the hard part, the difficult part for you as a student, is that you are going to have to know which H to solve for. So in this symbol that we are presenting to you, it's going to be consistent. There's going to be a capital H. That's the heat that we're solving for. And that makes a whole lot of sense. You may be unfamiliar or you need reminding what the triangle is. It's not saying that there's 3 or 4 different variables in this equation. We're not doing exponents while we're doing subscripts. That's not the scenario. This is just a bunch of information related to H. Capital H is heat. The triangle is the change. Because remember, heat is always moving from one location to the next. So what we will be measuring is how much heat was transferred. So that's why it's a delta. So heat is not stagnant. It is always moving somewhere. So we're going to measure how much heat was either absorbed or how much heat was given off. The little theta that's up in the air is more commonly symbolized with just a little 0. And what it's referring to are standard conditions. In other words, at 25 degrees Celsius. Now that's a hot day, but at 25 degrees Celsius, we could say essentially that's kind of like room temperature. That's where we're going to get a lot of standard values that we're going to use for our math. Now the X down below, you will never see an X related to the H. There are 3 at least that we will talk about today, and there will be a few more as we go along, different versions of H's that we can solve for. And again, that's going to be the difficult part as a chemistry student, is not just having one formula with the same variable. It's the heat of formation. It's the heat of reaction. It's the heat of solution. And each one has a different way to solve. So that's what we've got to try and accomplish. So as I previously mentioned, there's 3 different types of H's. I also mentioned that theta is more commonly going to be shown as like a degree symbol, a 0 at the top. And what that really is meaning is that they're wanting you to say, what were the initial conditions at time 0? All right, so here are the 3 different H's that we're going to have to solve for. They use abbreviations. And maybe it makes sense to you, and if not, let's talk about that. There is a delta H, a heat of friction, which is Try again. Reaction is correct. This is the heat of reaction. I like friction though, the heat of friction. That exists as well, I'm sure. Then there's the heat of solution. The heat of solution, that is correct. And then there's the heat of F, please. Ah, so close. It's a lowercase f, and it's not the bad word. Oh, far would be good. But it's not far either. Anyone out in the cyber world have a guess? Fluid, I like that too. Gosh, we've got so many F's. The heat of fantasy. I don't know.
Go for it. Say it loud.
Fusion.
Fusion is so wrong. No. Anyone else? One more guess. Let's make it fantasy. We'll use those gifted talents. Let's come up with the best F word that you can come up with. Frankincense is correct. The heat of frankincense. No, it's the heat of formation today. So it will be the heat of formation. I don't know why they were using all these funky abbreviations, why they didn't use FMT or something like that, but they use HF. So we're stuck with these symbols. Get used to them. We will see them again. All right. What are the units? I've already mentioned that the heat is going to be measured in something called a joule. What I did not mention, or kilojoule, what I did not mention is that we could measure it in something that you're very familiar with, a calorie. Here is the most common misconception. Have fun with this one tonight at the dinner table. I always encourage you to have, it's a Friday night, you're not that busy, there's not that many games going on, you might have a chance to interact with your parents. Ask them, what is a calorie? And watch them squirm because they won't be able to answer it because the most common response that you will find is, oh, it's that stuff you put in the food. No, it is the food. It is the energy in the food. If we literally take a piece of food and burn it, that bar that's coming out of the food, that's the calories. It's a unit that we can convert into joules. So if you notice down here at the bottom, 1 calorie is equal to 4.186 joules. So a calorie is a unit of heat. So when you consume food, you are literally measuring how much heat, how much bar is inside your belly. Now, I'm not trying to say that there's a roaring fire that's going on in your belly. No, but do you wonder how your body stays at a consistent 98.6 degrees? It's because you're consistently giving off heat from the food that you ate. You are consistently, and it's metabolic processes, I get that. But the basic idea is that you've got this churning bar in your belly and it's giving off heat. And that's how we stay at a consistent temperature because your body's regulated to continue burning a certain type of food at a certain rate. All right, now let me scare you. Oh, not yet. How do we measure it? And then I'll scare you. How do we measure it? There are these fancy devices. Some of yours at schools may have this one. This one is a heat shield. You could say that this is a calorimeter, but more classically, this is what a calorimeter looks like. But in both cases, what you do is you put food inside the device and you burn it. And then you capture the heat. You put a thermometer somewhere in here and it allows you to capture the heat. The same is for this device, but it more usually works with liquids. This one is something that you would do with liquids, but you'd still put some food measurable device in here and you burn it in there and it captures and it transfers all of its heat. I have a question from the audience. Yes.
How long do you have to burn it?
Oh, it happens very quickly. It happens very, very quickly. Just like if you were to, we could actually burn wood. And we could measure how many calories are in wood. Not that we eat wood, but you could measure how many calories, how many joules are in the food. So it's going to be fairly instantaneous. And we're going to do, I hope that your classes get the, and I know it's hard to compare yourselves, but I love my kids and I do some great experiments with them. I hope that they appreciate it. I hope you, and I'm challenging all the other teachers, burn some food for them, show them what a calorie is so that they get that relationship to it. Here's where I scare you. How many of you ate McDonald's this week? My class, every single one of them had their hand up. It is so sad and pathetic. So here's what you will notice from the nutritional facts. Actually, not a one of, they didn't want to admit it. How many of you, let me ask you this. How many of you proudly have ever had breakfast, lunch, and dinner at a McDonald's? On one day. It's the greatest accomplishment you can ever have. You feel so incredible after you come out of that final meal. You're just like, oh, what did I do? But so I just came back from France, and you're walking up and down the streets, and you're surrounded by these monuments and French people and everything. What was one of the first things I went and did? McDonald's at France. Yes. And they have macaron cookies at McDonald's. It's awesome. It's the greatest. Okay, here's where I scare you. Look in here. This is a medium fry. I know that you eat your fries. I know you love the fries. So do I. How many of you like to dip them in the ice cream? Like, yeah, that's the best. Yes, the goulash. Okay, well, this is just a medium, but look at that. You're saying, oh, you know what? That fat, that's not that much. That's 18 grams of fat. Let me put that in perspective. So that's a little glassy here. And you're like, oh, please, that's only a quarter of my day's allowance of fat. I can handle that. That's not that much. And you're saying, oh, look, there's just a few carbohydrates, 50 carbohydrates. And you're like, well, that looks like a lot to crunch on. I would feel guilty if I ate that much. Okay, so you're saying, I survived. I went to McDonald's. It wasn't that big of a deal. All right. Calories, though, if you eat the Big Mac meal. Like, well, heck yeah, I'm going to do that. And so you get your 58 grams of fat. That is a 58. That is, you would have to swallow that in 2 gulps. That is not a solid gulp of fat. You notice that is your daily intake of fat. If you go to McDonald's and you consume your Big Mac meal, and that's with a Coke also. This is also with a Coke, but this is the sugar that you consume whenever you eat a Big Mac meal with a soda. So put that into a little bit of your perspective. That's a lot of calories for you to burn off. Now, fortunately, you're young and you'll live forever, so don't worry about it. Folks like me probably need better choices, but will that stop me tonight? Do you feel better when you go to Chick-fil-A and you do the exact same thing? Yeah, you do. Yeah, I know. Or what's better is I somehow rationalize it. I'm like, hey, son, are you gonna eat your applesauce? And I just like steal, I'm like squirting that thing in there. I'm like, oh. Now it canceled out in all the other bad stuff. All right. How does your body deal with all of those calories? Well, we eat it and we put it somewhere. Oh, if this offends anyone, sorry, there's a nude person on the screen here. Sorry, there's no genitalia, so we're okay. But there is a consumption of the calories that's going on inside the body down here in the small and large intestine, stomach. It's all getting digested and absorbed. But how is it doing it? It's doing it through a chemical reaction. So our friends in the past slides here, we talked about the 2 endo and exothermic heat. So we know that endothermic is taking in heat. We're going to symbolize that with a positive. So mathematically, if you see a positive value, or if you're irresponsible like me and they just leave off the symbol, we got to assume that that means it's positive. But a positive heat, a positive joule, a positive calorie means you're taking in heat, endothermic. Negative means it's going to be giving off heat, exothermic. How will you see that is in the following 2 examples. Notice the placement of the heat value. It could be written as a triangle H equals -802. That's very clear and obvious. That is exothermic. What may not be obvious to you is that in the second line there, you notice that exact same value is written as a product. You have to interpret that to mean it's exothermic because it's being given off with the products. Even though it's not negative written there, it is implied that that means it's -802. But this author chose to write it in the scale along with the reaction. So you have to get that straight as well. Then if we go then to the endothermic, notice the value is positive. It is written with a delta H, but it will be written positively because it is a positive value on the left side with the reactants. So we have to relate the position in the reaction relates back to how we can view the value as exothermic or endothermic. All right. So now what if you had a jerk for a teacher? And what if they then decided to make this a little confusing? And they decided to not keep it the way it was normally. What if they put a negative in the reaction? So be careful. Notice in the third line, it's a negative 2870. What you have to interpret with that is that that author wanted the value on the left for whatever reason, but the reality is it's exothermic. It belonged on the right, but this author was so inclined, they just wanted to see if you were paying attention. So if you see a negative written in the scope of a reaction, flip it to the other side of the reaction. That means that this is exothermic. And then on the fourth line down here, the negative 34.5, that's implying that it also needed to be reversed to the reactant side, making it an endothermic reaction. Now, that's our first type of H. Here is your second type of H that exists out there. There is the heat of solution. Now, this one is no different from the heat of reaction, except for what we're dealing with. So it's only a heat of solution because there's not truly a reaction going on. All it is the particles, the CaCl2, they are dissolving, if you will. They are dissociating. The ions are breaking apart. That still requires energy. And so what happens in this process, either it's going to be taken in or given off, but it has a specific term that you should be aware of. It's called the heat of solution. So we have heat of reaction, and that involves the rearrangement of the atoms. This is a heat of solution value, and it only has to do with the fact that the particles are dissociating from one another. But as far as how we deal with the heat, did not change, just a slight difference in the terminology. All right, now we are ready to proceed with the formula, and this will be the last little pieces of the detail that we need to work with here. So what I've got is H could be written in one of different ways. And so be aware, there is a subtle difference between heat as an H and heat written as a Q. As a first-year chemistry student, I'm not going to even try to distinguish the two. The Q actually has a new term. It's called enthalpy or enthalpy, however you wish to pronounce the term. But you may see that the heat is being asked of you using the symbol Q. Just be aware, it's the same thing as an H. It could be a lowercase q, it could be an uppercase q. There is a subtle difference between them. It involves having the sum of internal versus atmospheric energy combined together. But for our purposes, we're just combining them all together. We're just going to call it H. We're just going to try and be consistent and make it simple that you're solving for H. All right. But that said, this was the slide that I chose that uses the Q. So just if you want to write this as H, I'm perfectly fine with it. This is the formula we will use to calculate heat. We're not going to be able to measure it directly. There's not just a conversion from temperature to heat. There's no way to go from T to J. We can't go from Celsius to joules. We have to go through this formula. So the conversion factor, again, ties in what Einstein talked about. We have to know the mass. And essentially what we're doing, the more temperature we have, we're measuring how fast the particle is going. So that's where the temperature comes in. The temperature, it says it can be in Kelvin or Celsius. Let's be consistent. Let's put it in Celsius. Maybe you can't see that underneath our pictures here. Let me slide that off down. So the temperature needs to be in Celsius. The mass needs to be in grams. The heat needs to be in joules. Well, that leaves us with this weird value in the middle called C. It is the specific heat capacity. And that's where the C comes from, is in the term capacity. I don't know why they didn't just call it SHC or something like that, or C sub HS. I don't know, but this is their choice and we're stuck with it. Many times you will actually even see that specific heat is listed as a CP, and I'll show you that one. So this is the same formula, just written in a more maybe clearer manner for you. You may approve of this one more. The color may appeal to you. I don't know. It's the same. Heat is equal to mass times specific heat times change of temperature. That specific heat value, it has some, if we wanted to rearrange this equation, what we would see is that it's heat divided by the mass times its change of temperature. So this is going to tell us what the units are. If we understand rearranging that equation, how we did that algebraically, all I did was move the mass and change of temperature underneath the heat. That will tell us what the units are. Hold on, I'll come back to this. The units for this specific heat are going to be in something called joules per gram degree Celsius. That's totally nonsensical. It tells you a little bit like this is a constant. This is kind of a made up number. This is something that they are using for us to help convert from Celsius into joules. It's very convoluted. What I want you to notice about it here are there are 6 different materials, substances with their specific heats listed here. And you can see they range from, relatively low at 500 for the diamond, all the way up to a really hot helium at 5,193. Well, what does that change in the values imply to you? What should you be able to interpret from that? Let's break that down right now. You should be able to look at a specific heat value and tell us if a material has a high specific heat, it is a good insulator. If we look at those values, it makes sense. Water, it holds heat very well. That's the reason why we like to bathe in it. Some of us like to get clean, but others of us just like to get warm. Again, how many of you just stay in the shower until your parents kick you out? Yes, that's what happens to me too. My kids, that I hear down the hallway. Oh, wait, what do you do? Okay, so my kids, they actually, for Father's Day, this is the meanest thing. They bought me a timer because I will run the heat. And so you'll hear it from down the hall. You're like, oh, I forgot, well, there's a little bit of heat. Now there's none, then you turn it off. But water holds heat very well. That's why it has a high specific heat. I know some of you are like, well, it figures, you're so stuck. No, I just like my heat. I don't know why. And then gold or aluminum on that list, it has a very relatively low specific heat. It's a good conductor. So low specific heat conducts heat. It goes right through it. It deals with the structure. If we talk about the structure, which we can mentalize, we can think about what, visualize. We can visualize what water looks like. Water is a chevron. And these metals are a series of connected spheres. They're all touching. That's why electricity flows through it nicely. That's why heat flows through it nicely. But water has these chevrons, and there's regions where there are pockets where heat can be trapped. So it holds its heat very, very well. So we see that in the data. Now, what are we going to do with all this? Well, we've got to do an example. So let me get over to my example here. So we are going to use that fabulous formula of, we're going to use the fabulous formula of H equals mass times specific heat times the change of temperature. So we got to first look in here, identify, well, where's the mass? Some of you are saying to yourselves, well, I see it right there. Here is where you got to be careful. I threw that in there just to trick you. What are we actually measuring the heat of? What is changing temperature? The water is. That's exactly right. We put 10 grams in there, but what's changing temperature? We're not touching the lithium chloride. We're actually touching the liquid solution. So what we're gonna do, and this kind of would be a little bit inaccurate, but because the specific heat would change once we added something into it, but we're just gonna discount that fact. What I need you to remember is the fact that 1 milliliter of water equals 1 gram of water. So I've got 60 grams as my mass. Now, my specific heat was given to me, and I would always give that to you as well in a testing scenario, in a homework scenario. You would always have it, or you could just Google it, 4.18. Now, you're saying, wait, that's 4,181. That's per kilogram. So what actually we need to do is we need to convert that per gram. And doing that, I've got it for you. It's 4.18 is the constant for water. Now, the temperature change, one of the details you need to know, it's final minus initial, final minus start, products minus reactant. That's going to be a theme that we're going to see in our heat unit. So I got 22.3 minus 20. We're going to put all those values together into a calculator, and we're going to end up with 576.84. But with sig figs, I guess technically we only have one sig fig, but let's just kind of ignore that. Here, we'll give it 3 sig figs. So we'll have 577 joules. Now, if I wanted to convert that into kilojoules, it'd be 0.577 kilojoules. It's that stinking simple. It's just plug and play. If you know the formula and you have the correct units, substitute them into the formula and you will be fine. All right, let's play a game. You're playing for fabulous prizes beyond your wildest beliefs. Beyond your wildest beliefs, okay? I'm sorry, you just can't even fathom what you're in for. Just think of the most great, generous offer possible that a teacher could ever make. It's beyond that. And they're bringing it Monday. No pressure. I didn't tell any of the sites this, but that's what's happening. All right. So what we're going to do is we are going to have some races between two sites and figure out who can get onto the broadcast the fastest with the correct answer. So it's a race between two different sites. And you're saying, well, who am I up against? Well, let's find out. Let's let fate decide us. Where are we going to compete? Are you ready? Oh, one of our sites isn't here, right? Is Spotsy's not here, correct? Yes, we can go. So whoever gets that one will have an automatic bye. It's like being in the tournament, right? They didn't have to play in the play-in round. All right, here we go. Who's going to play against whom? So we have, oh, it was close, but King George, you are on.
Hey, who said Spotsy's not here?
Oh, Spotsy's here? Oh, so sorry. Good. I'm
Here ever since the third slide.
all right. Good job. So you are in. You missed.
Stafford's not here.
I'm sorry, Spotsy, since you missed the first, let me just inform you, on the first slide, I was offering 100 bonus points. So you might have to take that up with Dr. Peppers. That's something that, it was just offered to all the other sites, if they could answer a simple question. So, Spotsy, you're gonna have to, ask Dr. Peppers for that one, okay? All right, so King George, who are you playing against? Is it? It is the Forge. All right. So Forge versus King. King and the Forge. All right. Let's go back to the question and let's see what we got here. So you have until.
Yeah, we have the answer.
297.
297.
Ford, 297.
27. You are the winner. All right. But wait. You're going to have to tell us how you did it. You can't just bust out some random, you guessed that answer. You're going to have to prove it to me. Come on.
Sure, I guessed it.
Tell me how you did it. What-
Okay,
All right, listen up.
so you have your mass, which there's no water or anything. It is aluminum, and you have 10 grams. Then delta T is equal to 55 minus 22, which is 33. Then you've got 0.9. You multiply this by 0.9, which is the specific heat That's basically 330 minus 33 if you want to do it in your head, and you get 297.
Oh my goodness. I am so, yay is right. So, the winners, your teacher will be bringing your reward on Monday, exciting moments for you, and losers, you can come over to their site and enjoy those same prizes, because we don't want to leave anyone out. That's a participation award. Yeah. All right, let's go to the second question. I'm not showing it this time, so you can't get a snapshot of it. All right, who's versus whom? Is that correct English? I don't think so.
Mr. Garrison, we have, the bell just rang here at Forge.
Oh, that sounds like an excuse. Bye. Riverbend, who are you playing against? Scotty, Dr. Peppers. All right, you can leave now, Dr. Peppers. You said you didn't want to be here when you're early. Now you can be there when you're late. All right, ready? Two sites, Ben versus Spotsy. It's a Spotsy-centric world here. All right, here comes your question. All right. Oh, wait, let's do it this way so I can write on it. Here's your question number 2. Go.
I think I could, but this number's big.
It's small. It is small.
46.
Got it.
What was it? What was that, Spotsy?
0.46.
You are correct. Very good. You are the wieners. Yes, yes, yes. All right. Explain to me, how did you get your answer, sir? What'd you do? Oh, you're about to lose your reward.
Oh, yeah. You were celebrating so much, we couldn't hear what you asked.
Oh, you better come up with an explanation. Show me your work.
All right.
Did it.
Right.
All right,
Tell 'em.
so there's 2 different ways you can do it, right? You can split it up and you can fix it through the version we did earlier. What
Okay.
I kept it original. So I kept the joules on the left side, okay? And I multiplied 175 minus 25. So that's 150. I multiplied the 150 times the 15.75. That will give me that times the specific heat capacity. And then I divided the left side by the right side and to get the heat capacity by itself. And that's how we arrived at the answer of 0.46.
Okay. Expertly done explanation. I am very impressed with you. 0.46. Great job. Spotsy, you are going on to the next round. You are wieners. Good job. All right. Race. Oh, I can't show you the question yet. Hold on. Let's do. All right. But we know who's playing in this one. It's the consolation bracket. All right. North versus Stafford. It's a Stafford-centric world. Let's see who's going. Oh, that's right. It's North versus Stafford. We don't need to spin it, do we? All right. Let's see if it actually, what happens when you spin. Oh, what's it gonna be?
Oh, man.
Oh, it's Stafford. Okay. Wow, it took it a while to tell me. Yay! Okay. North versus Stafford. Are you ready? Here's your question. Let's see what you can do. Race number 3. And I'm warning you, this one's challenging. It's not your straightforward question. Let's see you do it. Who is going to come up with the answer? Forge was not. Forge left. Oh, was it Stafford's not here? Well, they may be gone.
One is Spotsy.
Is anyone here from Stafford still or North? Okay. Here's the consolation bracket. Let's see who can come up with the answer first. All right, let's try. So here's your second chance at winning.
We've got it already.
Oh my gosh, what's your answer?
231.
That is actually correct. Very good. All right, so I'm going to save us a little bit of time here.
I got it too.
Good, very good that you also got it. Yes, very nice. So we take our heat, we multiply on the right side of the equation the mass times the specific heat that is given to you. And this time, here's the trick. I would solve for the delta T by itself, because then if you put in one of the initial values, solve for the final value, you're gonna have to deal with some algebra distributions. This is a much easier path, because if you do this, you then just solve for the fact that delta t is equal to 211. Now we know that 211 is equal, that's kind of hard to see, so let me scroll down here. 211 is equal to the final temperature minus the initial. Now this is just a very simple algebra. Move the 20 to the other side and you end up with 231 as your final temperature. Okay, this is everything that we need to know about making ourselves dangerous with respect to heat and how we can calculate heat. So I appreciate your time together today. Please badger your teachers and make sure that they give you some reward for being polite, for participating, and for winning. It's always better to be the, no, I'm just kidding. Everyone's a winner in my eyes. Thank you so much. Have a great weekend. Bye, you all. Oh, here, they want to see you. Do you want to see them? Yes, we want to see us. Your camera.
Oh, there's
No, your camera. Oh, they're gone. Oh, there it is. Okay, so let's go ahead and let's just talk about the lab for the next few minutes. Just kidding. All right, let's close out.